Good morning, YouTube.
Good morning, YouTube.
All right, what are we doing today? What are polar coordinates? Okay, so this is actually 12.3. I don't know why it says 12.2 here. Yeah, let's just say 12.3. What are polar coordinates? Well, it's really an extension of vector or parametric mode. Okay, so for example, this. Take a look at this. What if I gave you a circle? Can I do this? No, don't do that. Okay, there's a circle. And let's say it's centered at the origin. And it has a certain radius. In fact, how about we put the Cartesian plane over this? So you have an x-axis and a y-axis, right? So any point that you want to specify a location, you could uniquely specify it using x and y coordinates, right? But that's not the only way. This is an x and y coordinate, right? But let's say we're on the circle of radius r. And this radius, if I make a radial vector pointing to where I want to be on the circle, that makes an angle theta with the positive horizontal axis, or positive x-axis, right? So you could also uniquely determine a position by giving a distance from the origin and an angle. Yes? Now, is there a relationship between x and y and r and theta? What would you say is the relationship between x, theta, and r? Think of it this way. Here's a right triangle, because of your friend Descartes. There's always a right triangle. And this is x, and this is y, isn't it? So cosine, right? So cosine of theta is what over what? X over what? R. So what if I wanted just x alone? X would be what? R cosine theta. All right. So this is a convergent formula. If I know r and theta, I can convert to x very easily. Okay. Is there a relationship between r, theta, and y? Similarly, sine. So sine of theta is what over what? Opposite over hypotenuse, right? So y over r. And again, if I want to know what y is, it would be r sine of theta. Okay, so if someone gives you coordinates in r theta format, or polar format, polar notation, or what they call like you ever see these things in a old submarine World War II movie? They got the sonar going on. It's going ping, ping, yeah. Right? That's what this is. The polar graph paper doesn't look like horizontal and vertical lines. It looks like a pole. A polar axis, let me do it this way. A pole, no, stop it. There's your pole. There's your polar axis. And then you have concentric circles of 1 unit out, 2 units out, 3 units out, 4 units out. That's what radar looks like, right? That kind of thing. That's what we're doing. All right. Are there any other relationships here? Is there a relationship between x, y, and r?
Yeah.
What? All right, so I could say x squared plus y squared is r squared. So if I can give an x and y, I can convert to r. Or in fact, the square root of x squared plus y squared is r. So if I'm giving r and theta, I can convert to x or y. If I'm given x and y, I can convert back to r. Is there a relationship between x, y, and theta? X, y, and theta. Tan. Tan of theta is what? This theta. Opposite over adjacent, so y over x. So what if we wanted theta? How do you give it a tan? Don't say divide. It's not pre-calc.
Inverse?
What's inverse, right? You know how many times oh yeah, divide by tan. Okay. Because they think this means tan times theta. This is pre-calc, okay? You guys are way beyond that, right? Nobody thought that, did you? No. All right, so arctan both sides. Theta is the arctan of y over x. So again, if you're given x and y, you can use the arctan to get the theta. If you're given x and y, you can use basically the distance formula to get r. Okay, now knowing that, realize that this is parametric mode. Stop it. This is parametric mode. If I give you r as a function of theta, I could plug it into here in place of both r's, And then in parametric mode, on your calculator, graph x of t, y of t. But if r is the same in both, if y equals r sine theta and x equals r cosine theta, the r is the same in both, then you can use polar format on the calculator. Okay? So let's see how that works. What if we go, let's go straight to the calculator. Let's take a look at the calculator. Polar format. Let's see. Let's see what this looks like. Come on, calculator today. Yes. Come on. Come on, today. Today would be good. Wake up. Wake up. All right, so let's say I make a new document, and let's make it a graph. And let's change the type of graph. Wait, is it 3? Yeah. So let's go to parametric for a minute. So in parametric mode, you know, you can define a parametric trajectory. X is a function of t, y is a function of t, and they don't have to have anything to do with each other, right? Like y of t could be sine of t, and x of t could be e to the t, and you get some wacky, crazy path, whatever, right? But what if I gave you this? 3 cosine of t. Did I just do t like that? Yeah, okay. And let's say 3 sine of t. What's that got to be? Do you know what shape that is? Mother function. Notice what I just said. X equals r cosine theta. Here t is theta. And y equals 3 sine theta. What did I just do? Well, it could be. But if I say x equals r cosine theta and y equals r sine theta, what's r? 3. So can you think of a polar graph where the radius is always 3, but theta could be anything you want? So the radius is 3, theta is 0. Theta is pi over 6, theta is pi over 4, theta is pi over 3, theta is pi over 2. It's a circle of radius 3, isn't it? All right, it doesn't have to be a unit circle radius 1, but it's a circle centered at the origin. Now, is that true? Let's see. What if I just say graph that? There you go. It's a circle of radius 3. Dun, dun, dun. Okay. All right, there you go. Now, what if I change it up a little bit? What if I said, okay, tab, go back to the first one, and what if I don't make the r's the same? What if I make the r's different? What do you think is going to happen? That's going to be stretched out. So the x's can get up to 4 units far from the origin, and the y's can get up to 3 units from the origin, and that's a way to define an ellipse. Okay. And so you could do this in parametric mode, but you don't have to. Okay. Instead, what if we change the mode? Let's see. All right, let's do a new, okay, control, document, new page, another graph. Let's make it polar. Let's see. So let's make a polar graph. Okay. So now if I just put 3 here, what's going to happen? It's the same graph. What polar mode does for you is it takes the r and puts it in r cosine theta, makes that x of t, and it takes your r and puts it in r sine theta, makes it your y of t, if it's the same r. Now notice I could change the r, they don't have to be the same, so that would be parametric one. So there you go. Now there's all kinds of crazy forms you could get here, shapes. What if I gave you this? Let's see. How about 3, I don't know, plus, what do I want? Yeah, 3 plus 4, oh, I don't know, cosine theta. And here I'm in polar mode, so I better use theta. Where the heck is theta? Is it under the pi thing? There it is, okay. It's been a while. Okay. So now I got to use the theta key, okay? All right, so that's what I'm graphing. Now, I could do this in parametric mode. If I make x1 of t, that parentheses times cosine of t. And I make y of t, that in parentheses times sine of t. I could do this in parametric mode, but it's so much easier to do it in polar mode if the r's are the same. And we call that a cardioid with an inner loop. Notice it has horizontal symmetry, what if I change it up to, instead of cosine, what if I made it sine?
It would go the other way.
Whoopsie. I think it has vertical symmetry when you have a sine involved, right? Okay. That's a cardioid with an inner loop, also known as a limison, by the way. French word there. And I don't like where that arrow is. Can I get that arrow out of here? Okay, go away. Alrighty, now notice what we have here. We have, let's say if I call the A3, if I call 3, if I name it A and therefore I name it B, notice when B is greater than A, I have a limison. What if I have B is equal to A? Let's make them both 3. Look what you get. You get a cardioid, which, what do you think it's called, a cardioid? It's sort of like a heart shape, right? It has like that sharp corner there, like that. That's sort of like a heart shape, okay? So you have a cardioid with a sharp turn, or sharp dimple, they call it. A cardioid with an inner loop. What if I make, before we had B was bigger than A and B was equal to A. What if B is smaller than A? Let's make it, I don't know, 2. Right, so it's not a sharp dimple, it's just a dimpled cardioid. So that's a dimpled cardioid. The previous one is technically called the cardioid. And then the one with the inner loop has a special name called a limison. So there's all kinds of weird shapes like this. And what we're going to be doing for the next few days is talking about area of these kinds of shapes in polar notation, arc length, slope along the curve, that kind of stuff, okay? So the calculus of polar graphs, okay? What if I just gave you this? Let's see. Let me change this up to simply, how about just this? We have a circle centered at 1 on the y-axis. Okay. Let me think about this. Yeah, that's a good question. We could convert this back to Cartesian format and we'll see why. I don't know if I want to get into that. Maybe we'll do a little bit of transferring back and forth in a minute, but what if I did this? Take a look at this. Let's make, okay, tab. Let's make the radius bigger. How about 5? Okay. And let's do this. How about I put a 2 here?
It's a flower.
Yeah, they call it a rose. Yeah. Okay. It's a rose. Now notice the book calls, if you look at the book, do you read the book? No paper?
Yes.
Ink? Okay. You should become familiar with this paradigm. Yeah, so notice when this number here, I'm going to call this n. When n is 2, we get 4 petals. Have you seen this before?
No.
So what do you think is going to happen if n is 3?
6.
9.
You would think so. But no, it's 3. Gotcha. All right.
Higher on it becomes 2 petals.
All right, what if I make it 4 over here?
2 petals.
You think so?
I think so.
Got 8.
Wait.
Wait.
Maybe odds.
Odds?
Maybe
What?
5 would be 2 petals.
5 is 2 petals? Okay, let's find out.
5.
5 is 5? Yep. What's 6 going to be?
12.
12. So you got the pattern? Okay, so there you go.
What's the pattern?
Evens are times 2 and odds are themselves.
Right, so 12 and so forth. And so a typical question would be, on the AP exam, a free response question is, what's the area of one of these petals, for example? So we're going to talk about that. Right now we're just getting used to the idea of polar notation. Tomorrow we'll do area, and the next day we'll do arc length and stuff like that. It's not that big a deal, but one step at a time. Rome was built in a day, right? All right, how about this? Do you know how to graph something like this? What if I say 4x squared plus 9y squared plus 8x minus 18y minus 23 is equal to 0. Aha! What? All right, graph it. Go ahead. How do you graph that? would be nice to get y alone, but how the heck do you do that? Well, this comes under the heading of conic sections. You ever do conic sections? Ellipses, hyperbolas, parabolas? No? Conic sections? Conic sections in Cartesian form, x's and y's, can be written ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. Okay. If b squared minus 4ac is negative, you're going to get an ellipse. If b squared minus 4ac is positive, you're going to get a hyperbola. If b squared minus 4ac is 0, you might get a parabola, you might get the black sheep of the family. A degenerate conic, like a point. What's a degenerate conic? Can you think of a circle with no radius? What would that be? A point, right? That's a degenerate conic, right? So there's a lot of degenerate, a line, a straight line. They're all straight, thank you. They're a line, I did it. People do that to me all the time. Is a degenerate conic. Why is it called a conic section? Think of a cone, like an ice cream cone, but it's upside down. And you slice it. Let's say it's a solid piece of cheese or something. Solid piece of ice cream, okay? And you slice it with a knife, straight across, parallel to the base. And you take off the top. What shape are you going to see up here?
A circle.
That's going to be a circle. A circle is a conic section. Because you're slicing a cone. What if you sliced it a little bit off of parallel to the base? And then you take off the top. That's going to be an ellipse. So depending on how you slice the cone, you get different shapes. And if you slice it so that you just like, all right, how about this? A lot of times you see it done this way. Two cones, one on top of the other. Like this, eh? Right, sort of, yeah. What if you slice it right there, at that point?
2 points.
Well, it's just the 1 point, right? That 1 point, so that's your degenerate. What if you take your knife and you go right along the edge here? That's your line. What if you slice it like this? Yeah, that's a terrible.
It's supposed to be a parabola.
It's supposed to be a parabola, right? The side. If you slice it and you take off this piece on the left, this cross section here would be a parabola, right?
Yeah.
What if you slice it like this? That's a hyperbola. It's not parabolic. Okay? So the question is, how do you graph that? 4x squared plus 9y squared plus 8x minus 18y minus 23 equals 0.
Put it in polar form.
You could, but you don't have to do that in this case. But that is an option that's going to come up. All right, let's take a look at it. Let's do it this way. How about this? Let's start over with this thing. Okay, so if you did b squared minus 4ac, what would it be? Who's A, who's B, who's C?
A is 4.
A, B, C. A is in front of the x squared, B is in front of the xy term, C is in front of the y squared. So A is 4, B is 0, there's no xy term. Okay. And C is 9, so B squared is 0, right? Minus 4 times 9 is negative. So this should be an ellipse. Can you beat this into this shape? That's an ellipse. What's nice about this is standard form ellipse. H and K is the center of the ellipse, and A is a semi-major axis and B is a semi-minor axis, or whichever one is longer we call major. Right? So like with the ellipse that we drew that was 4 wide this way and 3 wide this way, this would be 4 squared, this would be 3 squared, and this would be 0, 0 if it's centered at the origin. Can you beat that into this shape?
You could try.
You could try. Well, you ever complete the square?
Yeah.
This has to do with completing the square.
I wish we did.
That's what we're going to do, real quick. Go away, go away, go away, go away. All right, so what about this? What if I regroup this stuff? What if I said 4x squared plus 8x, put the x stuff together, and 9y squared minus 18y, put the y's together, and let's just add a 23 to the other side. can you complete the square? Well, the easy way to complete the square is if there's a 1 in front of the square term, right? So what if I factor out the 4? What if you factor out the 4 from the x terms? What do you got?
X squared plus 2x.
Okay. Would you do something similar over here?
Yeah.
Factor out the 9. Okay. Now complete the square. What's squared? Now here's the trick. If you have a trinomial that factors such that both factors are equal, in other words, a quadratic that has the same root twice, repeated roots, that kind of thing. Remember, the pattern is that half of the b term, ax squared plus bx plus c, right? Half of the b term is in your factor, and that squared goes here. In other words, x plus 1 squared would be this. We got this. We're replacing it with this, but that equals that. So we change the problem. If you factor this, do you get x plus 1 squared? If I asked you to factor x squared plus 2x plus 1, would you say x plus 1 times x plus 1?
Yeah.
Or if you foiled x plus 1 times x plus 1, would you get, right?
Yes.
That's the pattern, okay? Now, it's really easy to force that pattern. But the problem is now I've added a 1 that wasn't there.
So you add it to the 23.
So I add it to the 23. What am I adding?
1.
A 4. Why? Because it's 4 ones, really, right? Because don't forget, there's a 4 in front of you, right? All right, do the same thing over here. 9 times what squared? How would you complete the square now? Y minus 1. And then if you FOIL this out, you don't get this. What do you get? Plus 1. So we changed the problem. So we added 1 here, so we better add 9 there, because it's really 9 ones in this case, right? And so if you add all that up, what do you got?
36.
36, right? Okay. Now remember, elliptic form had equal to 1 over here. I erased it, but, right, it was x minus h squared over a squared plus y minus k squared over b squared equals 1. How do you get that 36 to be 1? Divide everybody by 36. And you get x plus 1 squared over what? 4 into 36 reduces to what? 1/9, okay. Plus y minus 1 squared over 4 is equal to 1. All right, so how do you factor this thing? Where's it centered? I'm sorry, how do you graph this thing? Where's it centered?
1 negative 1.
Well, remember we're comparing it to x minus h over a squared. What's h?
Minus
Negative 1, right?
positive.
And k is positive, right? All right, so if h is 1, sorry, negative 1, and if k is positive 1, what's a? 3, and what's b? 2. So start at negative 1, 1 as the center. Go left and right 3. That's your semi-major axis. Go up and down 2, and you're done graphing. Right? Let's graph. Negative 1, 1. Go left 3. Go right 3. Go up 2. Go down 2. Connect the dots in elliptical fashion, unless you messed up like me. And it's something like that. Okay? So that's how you graph a conic.
H has been defined as 5 points.
That's sufficient. Yeah, usually that's enough. Yeah, did I mess up? What did I do? It doesn't quite look to scale. Well, it looks really bad, but you get the idea. Yeah. Did I go left and right 3? Oh, is that what it did?
No, I think you did.
Left and right 3 and up and down 2, right? From negative 1, 1? Left 3, right 3, up 2, down 2. It's my scale is messed up. It's too wide. Yeah, sorry, my scale sucks. All right, now, here's where it gets fun. That was easy. What if I asked you to graph this? No, not that. What's a good one? This one, okay. Let's say I want to graph that.
Okay, so A is 1.
A is 1.
B is negative 1.
B is negative 1.
and C is 1.
C is
So,
1. So b squared is negative 1 squared is 1. Minus 4ac is 4 times 1 times 1, so 1 minus 4?
Yeah.
Negative 3. It's an ellipse again.
Yeah.
But okay, what's the problem here? Can you, all right, how do you complete the square?
You have to separate.
Get all the x's over here, get all the y's over here. Well, but wait a minute.
You don't have
What about this xy term we didn't have last time? Remember we had a 0 xy last time? Ah, that's a problem. You can't separate that.
And now do you convert it to polar?
So now let's convert to polar. What did we say that x is? It was a while ago, huh? R cosine theta. So wherever you see x, write r cosine theta instead. That's a theta. Stop it. That's sort of a theta. Squared minus what?
R cosine theta times R sine theta.
Yep. Plus r sine theta all squared. And just for fun, I'm going to get the 12 out of the way. All right, so the idea here is to get r alone and graph it in polar format on your calculator. Let the calculator do it. Can you get r alone? GCF is r squared. Do you see it? There's an r squared here, there's an r squared here, and there's an r squared there, right? So if we take out r squared, what's left?
Cosine theta squared.
Cosine squared, right?
Cosine times sine.
Cosine times sine.
Plus sine squared.
Plus sine squared. Squared is equal to 12. So is it easy to get r alone? If I get r alone, I can go to polar format or even parametric format and graph this thing. All right, so what do you do? How to get r alone? 2 steps, right? Draw up a little more.
Oh, you divide by that long term and then
Divide by that long. You know, I'm lazy. I don't want to divide by that whole long. What is cosine squared of an angle plus sine squared of an angle, by the way?
1.
Well, I'm going to divide by that instead. 1 minus cosine sine? Is that what it is? So r squared is 12 over 1 minus cosine sine. But I don't want r squared.
So squirt it.
So squared it. Right. So r is the square root of 12 over 1 minus cosine theta sine theta. So we're going to get an ellipse. But what does it look like? If you can complete the square, if the xy term is not 0, you're either going to have horizontal symmetry or vertical symmetry for your ellipse. What happens here is you've rotated it. This is a rotation. Shall we graph this on the calculator? You ready? Yes, you ready? Got everything?
Wait, give us like 2 seconds.
Is there like a thingy rubber? Is there a, what is those things called? An equation sheet for the AP?
No, it's called your brain. Yeah, sorry.
So I just have to remember
All right, so let's go. All right, so how about, all right, let's just make a new page. No. Dang it. There you go. Graph, a new graph page. Okay.
Wait, can I just?
Now let's change this to polar format. What are you doing? What have you done?
Polar. R1 equals.
Just hit 4, right? Come on. All right, so is it going to graph R1 also? I still have an R1. All right, so what do we get? We got the square root of, how about rational? Control, divide. Of 12 over 1 minus
Cosine of theta times sine of theta.
Why are you stuck?
It's happening.
Don't ask me. I'm right
Oh my God. Okay, so
Rational.
where am I? This, then rational. Okay, 1 minus.
It looks like a thingy-mabobber.
That's very edifying.
It's like a tilted ellipse.
Right, it's a rotated ellipse. It doesn't have horizontal vertical symmetry anymore. All right, and we got to use theta here. So where was that? Where the hell was it? Here it is. Okay. I always forget what they put it on the nSpire. And times sine, right?
It looks like a solar system without all the other planets.
Well, yeah. Where do you think all this stuff came from? This was Newton and, well, Kepler, yeah. But Newton trying to figure out planet orbits and stuff. All right, so theta, where are
He's
you?
an astronomer as well?
Oh, he was everything.
I thought he was only a calculus.
No, he knows everything.
Oh, I thought it was just a crazy person.
And there you go. So you have an ellipse with a little rotational symmetry. Okay. All righty.
That's sick nasty.
This is crazy talk, right?
What graph was this?
Alrighty. We did that, we did that, we did that. We did that.
Alright, goodbye, YouTube.
We did that. Is it time? Is it time?
No, we still have 5 minutes.
Okay. Now, by the way, realize that when you get to graphing this, you really don't need polar notation. You could actually have graphed this in parametric notation and get the exact same thing. How?
Mr. Garcia.
How? Realize that polar notation is just parametric notation in disguise.
With the same R.
With the same R. So if you type this R, if you make x1 of t, this R times cosine t, because you're using t in parametric mode, right? And you make y1 of t, this R times sine of t, you should get the same graph?
Should.
Let's find out. So let's see. Let's make a new graph window. Skip that. A new page, a new graph window. Let's make it polar.
No, they say we're making parametric.
Oh, I'm sorry. That's right. Dang it. Parametric. Where's my parametric?
3.
3. There it is. Okay. All right. So it's the square root of rational 12 over 1 minus cosine. Now I'm going to use t's because it's a function of t in this window. That's all. All right. So t is just your regular t. All right, and times the sine of t. Then outside the radical, am I outside?
Times cosine of t.
Where am I? I want to be up here. Out, out, out. Okay, cosine. See what a pain this is? In other words, don't do this.
You're the one who wanted to do it.
I know, but I'm telling you, it's the same thing. What I do? No expression specified for y. I know, I didn't tell you the graph yet. Stop it. T. Aha. Boom. Okay.
Like copy and paste.
Now, you know what? Let's do that. Can I do that?
Copy and paste?
Um,
I don't think you
yeah, I
can.
can.
I'm just gonna, well, you waste your time trying to figure
How
out.
would I do that? I forgot how to do that. Oh, I'm just going to type it. Dang it. I forgot how to do it. So anyway, I'll figure it out. So control square root, control divide, 12 over 1 minus cosine. Oh, are we having fun yet? The point is don't do this. But you could if you had to. Early calculators didn't have polar form, didn't have polar notation. It just had parametrics. We had to do this.
It's like
Okay.
a desk right now.
Yeah, so
I
if
got
you're
the
stuck.
same thing.
Did you get the same thing? That's the point, yeah.
Yes. I'm still waiting for you, but.
I know, it's okay. Okay, so out of the fraction, out of the radical. And we're using t in this window. All right, so what'd you get? Ta-da, same exact thing. Okay,
Wait,
so
why is
if
it
the...
connected?
Huh? Well, it's probably, there's a problem with whether it's the... That's a fluke of the window. You can change the window, probably get that piece, okay? It's connected. Or maybe it's this thing getting in the way.
Text box, yeah.
Yeah, it's text
It's this,
box.
yeah. So anyway, so it's the same thing. It's a rotated ellipse. The thing is this: if the r's are the same, right? The r's are the same. Don't do this. That's silly. But if the r's are different, then then you got to do it. What if we had like a real parametric trajectory? How about if I said, okay,
Wait, how would we, if we converted it to polar and we did it like this, how would we get 2 different R's? Because when we solve them for R.
this one would be the same r. This has the same r. This
So-
particular one.
So I'm asking, like, how would we do it where we would solve for 2 different R's?
Well, they would give you parametrically x of t is this and y of t is this.
Oh, okay.
They would
and
just
then
give it to you.
use the
Yeah,
equation we
yeah, yeah.
started with.
So what if you had something like that? Okay, how about a new page, another graph, but this time let's make it parametric. Where am I? Parametric, and let's say it's something like, I don't know, t squared, and I don't know, sine of t. Just making up something.
Don't you have to times it by the things?
Well, this is like a whole separate thing. This is not polar.
Oh.
Okay, and let's see what this does for you. And so there's your trajectory. So you're trying to take off, and you sort of crash. All right, if you're a
Wait,
space shuttle,
Can
that's
you
not
use
good.
that to
Kinda
calculate
like my
air
legs.
resistance?
Yeah, yeah, oh yeah. We can work with the air resistance of these. Oh
Yeah,
yeah.
can you teach me how to do this? I can use it on my AP.
Not yet. I do stuff like that after the AP because it's not part of the course.
Okay, goodbye, YouTube.
Yeah, and I guess it's goodbye YouTube. Okay, so YouTube. I hope that was a fun time. Bye bye.